I'm going to take a look now at problem number 30 from the book. By the way, number 30 actually involves reference to L'Hopital's rule, which if you look up on the internet is actually very easy to work with. However, I'm actually not going to do part B, and I'm not going to require you to do part B because of the fact that we haven't actually talked about L'Hopital's rule. One of the drawbacks of skipping around in the book a little bit. Same type of thing as question number 29. It asks you to use derivatives to find the x-coordinates of the critical points of f and f prime. So we're going to find the derivative here. The derivative, of course, derivative of the first times the second plus the first times the derivative of the second. I'm going to do this up to the side here. That's going to be x squared times 1 over x, which, of course, is just going to cancel out to leave me with x. So my derivative there is going to end up being 2x ln of x plus x. Now, my critical values are going to take place where my function is either undefined or where it is equal to 0. So set it equal to 0. And basically what's going to end up happening here is I can factor out a value of x, and we're going to get 0 equals x times 2 ln of x plus 1. So either x is equal to 0, and actually that's one of the places that the natural log function is undefined as well. It's defined only for values greater than 0, so that covers that as well. And then second of all, I want to figure out what's going to make this equal to 0. So I'll set 2 ln of x plus 1 equal to 0. That means that 2 ln of x would equal negative 1. And then I can divide both sides by 2. And that's going to tell me that ln of x is equal to negative 1/2. Okay, if you go back to Algebra 2, you remember that a natural log is really just a log base e. Okay, my general rule is anytime you got something in a log form and you don't know what to do with it, switch it to the other form. So this is a log base e of x equals negative 1/2. We have a base, logs are exponents, and I have a result, and it basically tells me that x is e to the negative 1/2 power. And by the way, e to the negative 1/2 power is equal to approximately 6065. So it gives you a little bit of an idea there about what's going on. So my critical value here is going to be basically this e to the negative 1/2, which is 0.6065. Again, I'm not going to use 0 because the graph actually isn't defined at 0 at all. It's not to define 0 or values less than that. So essentially we basically just have a graph that cuts off there, so we're not going to have a cusp or any kind of change in direction happening on the other side of 0. So we just have that e to the negative 1/2, which again is about 6.06. If we want to put that value in. If I want to test values here, I can put different values in. I think it's easiest to use the factored form of the function. This is about 0.606, so if I put a 1 in here, for example, ln of 1 is 0, plus 1 is 1, times 1 would give me a value of 1. So that would be a positive value, it's going uphill. Meanwhile, if you put a value less than this, if you put something like 1/2 in here, for example, you're going to end up getting a negative value coming from this, which multiplied by 2 is going to give you a negative value here, and then when you multiply by that value there, you're going to end up with a negative value. So it's going to be basically downhill and then uphill. And actually, if you look back at the original graph in the book, you're going to see that you end up having a relative minimum here at that point where x is equal to about a little bit more than 0.6. Okay, so that's my first derivative and the background behind it. To find my second derivative, I'm going to come back in here and erase what I've got here so far. Look at the second derivative. Second derivative, I'm going to need a little bit more product rule here. Derivative of the first is 2 times the second is ln of x. Plus the derivative of the second times the first. Now that's going to be 1 over x times 2x, which when we cancel the x's is going to end up just being 2. And then plus the derivative of the x, which is 1. I want to figure out where this is 0 or undefined. So 2 ln of x plus 3. And same kind of thing here. The natural log function is only defined for values greater than 0. So we have that kind of cutoff point there at 0. Again, we're not going to have a maximum or we're not going to have a change in direction there. I guess we could technically have a maximum or minimum at an end point, but I'm not going to be looking at that in this problem. Basically, I just need to figure out where this is going to be 0. So -3 is 2 ln of x. I can divide both sides by 2. Okay, it's the same thing as before. I have ln of x equals -3/2. A natural log is a log base e. So I have a base, an exponent, and a result. So I know that e to the -3/2 is my value of x, and that's going to be my missing value. By the way, e to the -3/2 is approximately, this number written down here, it's about 0.2231. Okay, so again, that's a positive value. And so I can do my second derivative table here. And we can see here that at a value of about e to the -3/2 power, which is about 0.2231, that's where that point's going to take place. If I put a value greater than this in, like if I put 1 into this function, for example, we can see up here, if I put 1 in there, that's 0, we get an answer of 3, so it's going to be positive, and that's going to be concave up. And then we can see here, if I put a value less than that in here, let's put in something like put in an x value of something like 1/4 or something like that. You can see that 1/4 is still going to be greater than that. Like 1/10, it's going to be a very large negative value plus 3, and it's going to end up being negative. So we get something that looks kind of like that. And again, if you take a look at the graph in the book, the function that they give you in the book looks something kind of like this. They've got a point plotted at 1, they've got that on each axis. The graph basically is undefined here, and it loops under, and it basically does something that looks kind of like this. And so you should be able to see these points coming into play here. There's your point at about 0.0, or about 0.6, where you basically hit a minimum value. Okay, and so we can see the graph goes downhill, and then we can see the graph goes uphill. The concavity change is very, very difficult to see here in this function. But basically, we have something that is concave down. We can see pretty clearly that it's concave up here. Apparently, the graph is concave down. It's probably doing something more like that and then going around. So a little bit hard to see that picture, and I think in part C that's what they're getting at. They ask you if there are any other critical points that don't show up on the graph. Well, no, we found all the different critical values for this graph. However, it's very, very hard to see that this graph is apparently briefly concave down, and it's in such a small range of x values that you're not really going to see it in the equation. So that's another case where you can see things using the first and second derivatives that you're not necessarily going to be able to see using a graph, which is part of the reason why this number line idea and using first and second derivatives is so incredibly powerful.